Good morning, friends. In today's lecture, we will start the Laplace transformation. First of all, let us start with definition of Laplace transformation. Let ft be a function of real variable t, and it is defined for all t greater than or equal to 0. Then the improper integration 0 to infinity e raised to minus st ft is known as the Laplace transformation of function ft. Here we provided that the integral is exists. Its existence condition we will see later. First of all, how to denote the Laplace transformation. Laplace of ft is denoted like this, and after applying the Laplace integration, that is integration 0 to infinity e raised to minus st ft dt, we get the sum function of s after putting the limit. First of all, solve the integration, then put the limit 0 to infinity, and as a result we get some new function of s. So it is a one type of transformation from function of t variable to function of s variable. As a, here our input is ft, that is in terms of t, and after applying the Laplace transformation or this integration, we get output in the terms of s. That is a main concept of the Laplace transformation. Here we are converting the function of t into the function of s. Let us see some linear properties of Laplace transformation. Here Laplace of ft plus or minus gt is equal to Laplace of ft plus Laplace of gt. We can separate the Laplace and then evaluate that. We get f bar s as a Laplace of ft and g bar s as a Laplace of gt. So finally we can say that Laplace of ft plus or minus Laplace of gt is Laplace of f bar s and g bar s. Now Laplace of alpha times ft, here alpha is any real scalar, then we get Laplace of alpha times Laplace of ft, that is alpha times f bar s, that is our linear property for the Laplace transformation. Let us see some examples of the Laplace transformation. Here we can take some discontinuous function as well as continuous function for the Laplace. First of all, find the Laplace of ft, where ft is discontinuous function. In the interval 0 to pi, our function is sin t, and pi to infinity, our function is 2. Now, how to find the Laplace of this discontinuous function by definition? First of all, we will write the definition of Laplace. Laplace of ft is integration 0 to infinity e raised to minus st ft dt. Here our function is discontinuous, so we divide into two parts. First part is 0 to pi and its function is sin t. So here first part of the integration is 0 to pi e raised to minus st ft dt, and then pi to infinity e raised to minus st ft dt. In this first part we are taking the function sin t, and in the second part we are taking the function 2. So our Laplace of ft becomes 0 to pi e raised to minus st sin t dt plus pi to infinity e raised to minus st 2 times dt. Now evaluate the integration. Laplace of ft is equal to e raised to minus st upon s square plus 1 into minus s sin t minus cos t. Here we are applying the Laplace integration e raised to ax sin bx is equal to e raised to ax upon a square plus b square a sin bx minus b cos bx. This integration applicable, this formula is applicable here for this integration. Number 1, Now, second integration is very easy to common outside, and integration of e raised to minus st is e raised to minus st upon minus s, and 0 to infinity. Here our variable is t and its coefficient of t is minus s, so we are dividing by s here. Now we will put the limits of this integration. First, in the first integration, upper limit is pi. So first of all, we will put the limit of pi in this portion of integration. First part of the integration, it will be e raised to minus pi s. Remember here, variable is t, so we are replacing t by pi, e raised to minus pi s upon s square plus 1 into minus s sin pi minus cos pi. That is our upper limit of the first integration. Now put the lower limit in this portion, that will be e raised to minus 0 upon s square plus 1 into minus s sin 0 minus cos 0. That is our lower limit of the first integration. Now we will put the upper and lower limit in this integration, as we know that e raised to minus infinity is 0. So first limit will be 0 when we are putting e raised to infinity in this portion, because e raised to minus infinity is 0. So we directly write down here 0. Now lower limit is minus e raised to 0 upon minus s into 2. That is our lower limit. So its upper limit is directly 0 and lower limit will be this. After simplifying this upper limit, here sin pi is 0, so this term will be 0. Cos pi is minus 1, so this term will be minus 1. This is as it is, and e raised to 0 is 1, so it will be 1. Sin 0 is 0, so this term will be 0, and cos 0 is 1, so we are writing here 1. Here in the second integration, first upper limit is directly 0 and minus minus plus, so our last term is 2 by s, because e raised to 0 is 1. We know that e raised to 0 is 1. So finally, this is our simplification of this upper and lower limit. For the mod simplified, after mod simplifying, we get e raised to minus pi s upon square plus 1. This term is directly cancelled, and this will be minus minus plus 1. So first part is this e raised to minus pi s upon s square plus 1, and minus lower part is only 1 upon s square plus 1 minus minus plus. So finally this minus and this minus is plus, so finally we get this integration answer e raised to minus pi s plus 1 upon x square plus 1. That is our first integration, and second integration is 2 by s only. So hence our final answer is Laplace of ft is equal to e raised to minus pi s plus 1 upon s square plus 1 plus 2 by s. That is our Laplace integration. Let us see one more example of same type. Laplace of ft is, find the Laplace of ft where ft is t from 0 to 3 and 3 to infinity is 0. Here function is also discontinuous. Now we will take the Laplace by definition. First of all, Laplace of ft, this is the definition of Laplace of ft, integration 0 to infinity e raised to minus st ft dt. It is divided into two parts, 0 to 3 and 3 to, here we have a 0 to 3 and 3 to infinity. First of all, 0 to 3 e raised to minus st. Of first function is t, so we are writing here t. This is our first function for between 0 to 3, and 3 to infinity it is 0. So this whole integration will be 0 in the next step. Now we will put the we will solve the only first integration. Here we have a two functions t and e raised to minus st. First function is algebraic function t, and second function is e raised to exponential function e raised to minus st. So we are applying the integration by parts rule. Integration of u into v dx, that is equal to u integration of v dx minus derivative of u, that is u dash, integration of dx. This is our first integration, and we are directly put here integration. Then again we are taking the integration. That is our L'Hopital's rule for the integration by parts. Now first we are taking here u equal to t and v equal to e raised to minus s t. So first u as it is, that is t as it is, integration of v, that is e raised to minus st upon minus s, minus derivative of u, that is derivative of t, that is 1, and integration second time of this function. The integration of this part is again e raised to minus t upon minus s the whole square. So the next step, we will put the limits, and second integration is here directly 0, so I am not writing here. Now we will solve this only this integration. First of all, put the limit, upper limit 3 in place of t. First 3 into e raised to minus 3s upon s minus 1 into e raised to minus 3s upon s square. We will replace t by 3 in this portion, this integration, and in the lower limit we replace t by 0. Then we get this part 0 into this function e raised to 0s upon s minus 1 into e raised to 0s upon s square. Now after simplifying, we get after putting the upper limit we get this part, and lower limit is this. Now simplify this portion. This will be 3 times minus 3 times e raised to minus 3s upon s. This will be minus 3s upon s square, and this portion is totally 0, and minus minus plus, then we get 1 upon s square, because we know that e raised to 0 is equal to 1. So finally answer of this function is e raised to minus 3 e raised to minus 3s upon s minus e raised to minus 3s upon s square plus 1 upon s square. So these are the some concepts of Laplace transformation by definition. Now we will discuss. Now when Laplace transformation of any function is exists, here sufficient condition for the existence of Laplace transformation. First of all, our function should be continuous or piecewise continuous. Here meaning of piecewise continuous function, that means our function is continuous in the sub intervals. Here first interval is from a to b, and in this portion function part, first part of the function is continuous. This is the part 1 of the function is continuous. This portion is second part of the function, that is also continuous between b and c, and third part is continuous in between c and d. That means our function is continuous in the sub intervals finitely many times, then it is known as piecewise continuous function, and that type of functions can be that type of function have a Laplace transformation. And second and important condition of the Laplace transformation is ft is exponential order of alpha. That means there exists some m. Here m is any constant. Alpha we have to find m and alpha in this portion, and the whole function is smaller than m into e raised to alpha t for all t greater than or equal to 0. In other words, we can say that limit of t tends to infinity e raised to minus alpha t into ft, this should be finite, then we can find the Laplace transformation of ft. These are most important conditions, but that is can we can solve by theorems. Here we are not concentrated on this portion majorly. As for example, Laplace transformation of tan t is not exist because tan is not piecewise continuous function, and during the for all t greater than or equal to 0, and second is e raised to t square, we cannot find the finite limit of this function ft into e raised to minus alpha t, because therefore Laplace of these two functions is not exist. Thank you.